Okay, so reductions and oxidations or more fun with carbonyls, and I'm going to very quickly pull up and figure out where I left off last class because that would have been a smart thing to do in the last 15 minutes. But, you know, it's been a busy week. Okay, we were talking about Leo the Lion says Gur, and we were talking about oxidation reduction profiles of carbon dioxide. No, methanol, one carbon methane. So I think near the end of last class, we were talking about sodium borohydride and the reduction with that. So what I want to talk about here is I want to bring up this chart again of, I'm just going to keep it real simple. R is just anything, any carbon chain. I'm not defining what it is. So last class we talked about sodium borohydride. And what we were saying is basically the H minus is attenuated because it's bound to the boron. So it's got this covalent bond, so it's not really H minus, but kind of is H minus because the boron wants to lose H minus. So it's kind of sort of maybe H minus. And it's attenuated by being bound to the boron. I'm going to come back to this slide throughout the class today. So I'm just going to leave it there for now, and we're going to flip ahead and I'll flip back. So next reagent I want to talk about actually is the question I just got, which was lithium aluminum hydride. So this looks a lot like sodium borohydride. It's aluminum with hydrogen. And a lithium nearby. So if you look up your handy periodic table, which I don't have handy, so electronegativity periodic table. Pulling up electronegativity periodic. Okay, there we go. No, I picked one like on Pinterest or something where I had to buy, and so it just bullshit. Okay, so those of you keeping track at home, boron is 2.0. And so for context, carbon is 2.5. Aluminum is 1.5. For context, lithium is 1.0. So if we're looking at that, and I'm thinking big numbers mean more electronegative, small numbers mean more electropositive. Aluminum is more electropositive than boron. So now I'm already thinking that aluminum is getting pretty unhappy with that negative charge compared to boron, because aluminum is a lot more electronegative, electropositive. So this is reactive. More reactive than sodium borohydride. Because these are electronegativities. So, yeah, if you don't have one, I found mine on Google. Okay. That should be lithium. And what did I do? Did I just delete the entire slide? No, I didn't. Good. There's no silicon anywhere here. I just wrote context. And I didn't write any neater. There, the cursive is better. So just comparing, boron is a little less electronegative than carbon. Aluminum is a little more electronegative than lithium. So with that in mind, this is like sodium borohydride on steroids. but the mechanism is identical. So let's say we have an ester. It's floating around, minding its own business. Some organic chemist dumps in some lithium aluminum hydride. You know what? I write cursive A, but it's very confusing. And what's going to happen? I'm going to use a lone pair from hydrogen. We're going to attack this carbon. Now, with all this talk of LUMOs and HOMOs, you're going to attack the LUMO, and the LUMO, you're going to donate electron density to the LUMO, and that's the antibonding orbital of the pi star. So you're going to break the double bond. In general, you break double bonds first. So we make that. Okay. So one thing we haven't talked a lot about, and this is why, and we're going to spend a little bit of time on this today. Carbon doesn't like making two single bonds to oxygen. That's why ketones and aldehydes exist. You don't have two single bonds, you have one double bond. So this doesn't want to be like this. It's going to put the electrons back in. And we're going to lose O minus. Because of everything I can break, if I'm going to do that, I have to break a bond. And of all the bonds I can break, O minus is the best thing to lose. Okay? Now, what I want you to think about, call this A, I'm going to call this B. And I want you to think about this carbon. Which of those carbons is more positive? Which one of those has a greater positive delta plus on it? Okay, we're getting a lot of A's, we're getting a B, getting an A. Any C's? Okay. A for sure. I think Muazzam has actually answered both. Yes. Okay. Clever way to hedge your bets. So, so let's think about the charge density on this. So if you think of the resonance structure that's available to an ester, okay, we can polarize that bond. And we can draw a positive charge here. But then that's in resonance with that. Whereas this guy, we don't have any other alcohol to help us out. No resonance. So, you're like, okay, well, resonance is good. Resonance is stabilizing. And I completely agree. Resonance is stabilizing. The ester is more stable, for sure. As much as we can talk about the stability of neutral compounds. But is that positive charge more on a carbon? The answer is no. Because this positive charge can localize off to this oxygen, which is, an 8 electron stabilized oxygen. So effectively, this oxygen up here can steal electrons from this carbon, from this double bond, and this carbon can steal electrons back from this oxygen next to it. That is not open to this carbon. Once this carbon has its electrons stolen by the oxygen, that's it. Electrons are stolen by the oxygen, and it's sitting there sitting with this positive charge. So this is more positive. more electronegative. Like electrophilic. It's like electronegative is not the word I meant to say. It is tough. It's hard out there for aldehydes. So you have to now. This is a different logic that we went through when we're talking about stabilizing a positive charge that is actually there. If we're trying to stabilize a positive charge that's absolutely actually there, more resonance is great. And the reason why more resonance is great is because we're dispersing the positive charge. And a positive charge prefers to be dispersed, so it's going to happier there. We don't have a positive charge here. We're creating one. And what we're asking is, where is it more likely to be formed? When we think of it that way, it's more stuck on this carbon for this guy, for the aldehyde, than it is for the ester. Okay, so with that sorted out, let's say you have an excess of lithium aluminum hydride. So let's say you got, we'll do this like really, simple math. You got 10 molecules of lithium aluminum hydride, and you have 10 molecules of this initial ester. This reaction happens once. Now you have 1 molecule of this aldehyde, 9 molecules of lithium aluminum hydride, and 9 molecules of the original ester. What does your next molecule of lithium aluminum hydride want to react with? Cat got your fingers? There we go. It all came out. Yeah, exactly. It's more positive. It's the better electrophile. It's the more reactive site. So lithium aluminum hydride, when it's not flipping back and forth between previous slides, does the same thing again. And we get the alcohol. So what this is telling us is that aldehydes and ketones are more reactive towards nucleophilic reducing agents and nucleophiles in general than esters are. I would expect the aldehyde and the ketone to react first. So you actually need a more potent reducing agent to reduce an ester than you do for an aldehyde or a ketone. And we can see that if we go back. Oh, come on, it flips back and forth when I don't want it to. And that's that lithium aluminum hydride can reduce you from, I'll make it, you actually can reduce acids, we need heat. But let's take it to an ether. So it can reduce esters down to alcohols and aldehydes and ketones down to alcohols. Whereas sodium borohydride is not as reactive. Because again, not as reactive because the boron is more electronegative, so it can share more of the electrons with the hydrogen, so the hydrogen doesn't get all the electrons. So it's not as H minus C as it is when it's attached to aluminum. And so sodium borohydride on its own will not touch an ester. It will only touch a ketone or an aldehyde. Ethyl is ethyl. Sorry. Back in the naming slides near the beginning of the course, I gave for anyone who's confused, I'm going to go right back to, I'll go right back there. For anyone who's confused, I gave a list of number of carbons and then the abbreviation that gets used for that. So methyl, ethyl, propyl, butyl, pentyl. The only two that we really use a lot are methyl and ethyl, Me and Et. The other ones we tend to write out. Yeah, you can use tert-butyl. Like I'm going to be marking, we're going to be marking those by hand. So if it's IUPAC or IUPAC light, like, and follows the rules, we'll accept it. Interbutyl is acceptable. I guess it's not IUPAC, but fuck IUPAC. Okay, so this is lithium aluminum hydride. Um, well, sometimes things get more complicated than they need to be. Things can be simpler. There's no reason to overcomplicate something, and calling something a terbutyl is a lot better than calling it a 2 dimethyl propyl group, which is silly. So you don't need to see who's changed my Dropbox. Okay. Um, why does oxygen have a positive charge? Where? Here? That's negative. That's negative. It's just I'm not very good at drawing. No, oxygen's not positive, it's negative. And then water comes in. Sorry, I think there was just a little cross there because my pen slipped. And you get just the neutral OH. Again, we're always looking for neutral products at the end of reactions. We don't want to leave charges lying around. Yeah, I'm very sorry. You're right. You're not confused. You're correct. Everything does make some sense. So we can use. There's actually a reagent that can take you from the ester down to the ketone aldehyde, but I'll leave that for a later course. We're not going to talk about that. I just wanted to talk about those two reducing agents. And what I want to talk about now is going in the other direction. So what if you have an alcohol and you want to turn into an acid? So you want to go up the oxidation chain. Well, the reagent we're going to use is called the Jones reagent, which who cares? Well, Jones probably cares, but he's dead. So we have, this gets referred to though as the Jones reagent. It's bright yellow, orange. You mix chromium trioxide, which is really, really toxic, with hydrogen, with sulfuric acid, which is really, really corrosive, to get a really, really, really toxic, really, really, really corrosive, really, really, really oxidizing mixture, which basically destroys all sorts of stuff. So this is going to take us to a carboxylic acid. So how does this work? Well, first of all, I don't like this because, and of course, there's a little bit of water in here too, because there's always water. Because chromium makes way too many bonds. I start getting nervous when I have to count more than 4. And I think that's 6 if I can count that high. And so what we're going to do is we're going to throw acid in here and water. So here's a rule of thumb. If there's a charged thing anywhere, and especially like H plus, which is hidden, it says H2SO4, but that's H plus. Use that first. And the reason for that is normally when you add acid to a reaction, you add acid to make it go, to initially raise the energy of something so something can happen. So when in doubt, protonate things, like throw an H plus on something if there's H plus around, or use OH minus to remove an H from something. Always a good first step if you don't know what else to do. So following John's law of protonate things, we're going to protonate things. See, I really want that to be carbon because carbon is a sensible element. It's not trying to poison you with its heavy metal. Take care of that. Okay, now chromium is making way too many bonds. It's got way too much stuff attached to it. I'm an organic chemist. I believe carbons are greater than metal. Carbon's my favorite element. It's really boring. Though diamonds are nice. Cool. So this is basically what we're making the Jones reagent. And it makes in situ when you add sulfuric acid to chromium. Okay, that's fine. Um, doesn't really help me um, because why does water attack the chromium? Because chromium doesn't want to be attached to an oxygen with a positive charge with a double bond. I think we're changing the geometry of the chromium, and I'm going to leave that to my colleague, Dr. Marcus Drover, to discuss the geometry of chromium 6 versus. These are two different geometries. One is trigonal-planar, and one is, I think chromium 6, like this guy here, I think it is um, almost tetrahedral, but I'm not 100% sure. I've never thought about it because I really just do not care, is when it comes down to it. So I've got this, I've got my alcohol, and I don't currently have an acid. But this whole oxygen making bonds to chromium thing is what we're going to do. So I'm going to do what's called proton transfer. So what does this mean? This means I'm going to move a proton around. Now, what people do wrongly is when they want to do this, they'll draw, and this is wrong and it really upsets me. They'll draw this to get to the product. That is wrong. The reason that is wrong is because that is a four-membered ring. That strain is ridiculous. Like, it's just insane. Um, and I would be slightly more forgiving with this because you have a chromium as one of the atoms. But that's generally not how this happens when these kinds of things happen. What happens instead, and you can actually figure this out by actually like labeling atoms with like radioactive isotopes, is a water molecule is going to come in and remove that hydrogen, and this is going to grab a different hydrogen from solution. Now I can just write proton transfer. I've just shuttled the hydrogen around onto this guy. I've moved the hydrogen from one oxygen onto another oxygen. Now I'm going to flip to a new slide because I'm learning my lesson. I don't want these too crowded. And now my alcohol is floating around. Yes, I can. I can if I can figure out how. Um, I want to go back. There we go. Welcome. Okay, so we have this alcohol floating around. I made it a primary alcohol. Now, we just had water attack chromium. You know, what's another oxygen between friends? I hate metals so much. So now we have this. Going to do another proton transfer. Notice I'm putting these in using equilibrium arrows. I'm saying this goes back and forwards because all proton transfers always do. And I'm sick of writing proton transfer like that, so I'm going to abbreviate that as PT. And that just allows me to move protons around. What do you mean next class? Okay. No, I meant it will come up later this class. There's a lot going on. I am sympathetic. There's a lot going on. Clever. You're a very clever person. So, what we have here is a mess. Now, remembering where we're going, we are going to try and make an acid. And what that means is these two hydrogens I've drawn in need to be taken away and replaced with bonds to oxygen. And this is our first chance to do that. So we're going to use water as a base. Taxes hydrogen. The electrons in the hydrogen-carbon bond make a carbon-oxygen double bond. That's forcing the oxygen to break a bond. It's going to put some electrons onto chromium, and then the chromium is going to lose water. So let's just number those bond arrows. This looks kind of complicated. It's going to make a lot more sense. I'm going to make a note here. This is an E2 elimination. We're going to come back to what that means. So we're going to spend about a week and a half on E2 eliminations. Starting in about a week. So just when you're looking over your notes after you talk about E2, you go, oh yeah, that is an E2. That makes sense. So what we have coming out of this, though, is we've just made ourselves an aldehyde. Plus, if we follow all the bonds that the chromium's making, it's gone. Now, there's a bit more time than a week and a half left in the semester. Not a lot more, but there's more than that. And we have chromium 4. About 2.5 weeks. Yeah, metals suck. So, okay. Now what happens? Well, we're not in acid yet. We're only in an aldehyde. So what do we have in solution? Well, we got lots of acid, we got lots of water, and we got more Jones reagent. So first thing we're going to do is let's just have some Jones reagent hanging out down here that we made previously, mechanistically. We'll stick a proton on there. We'll have it all waiting for us. Now, last time we would have had the alcohol. This is this guy up here in the top left-hand corner down here. We had the alcohol attack. Now, aldehydes aren't all that good at attacking. Proton transfers are always happening. So normally if I don't do the proton transfer, the thing that's going to happen is I'm going to go back the previous step that I made. Like it's just going to undo what I did, and that's likely to happen. All this stuff kind of is in equilibrium until this step here. This is the end of the road. This is irreversible. But actually, all these steps are in equilibrium. I just didn't draw equilibrium arrows for everything. That can go backwards. Like the most likely thing to happen is for the arrows to push exactly backwards from what we saw here, kicking the alcohol back out. But if I don't want that to happen, if the proton moves, and protons are always moving, then I can get to a place where suddenly I get to a point where I do this reaction, suddenly it's irreversible. So everything's kind of switching back and forwards constantly until you hit a point where, okay, it's over. We've just done something irreversible. We're going to come back to what that means too. So in this case, you know what? I'll be careful with my equilibrium arrows. Theoretically, everything is in equilibrium of some form. Just sometimes it's meaningful and sometimes it's not. Oops. When in doubt, protonate something. Got it out. I can feel the doubt through the Zoom channel. Okay, I just said this is bad. Carbon doesn't like making two bonds, single bonds to oxygen. It wants to exist as the aldehyde. Yeah, that's absolutely true. But I need an alcohol to do the next chemistry. And all aldehydes exist a little bit of the hydrate, and this is the hydrate. Every aldehyde has a bit of hydrate in it at all times, about 0.1%, give or take. Now I'm just going to have water come in and scoop up this extra hydrogen because it's in my way. And so I'm going to have the true hydrate before it rapidly decomposes and goes back to being an aldehyde, because that's what it wants to be. It really doesn't want to be a hydrate. But, if I have the Jones reagent in here, we've got options. Sorry, magically one of my hydrogen became a carbon. That is not magic. That is, I am incompetent at drawing. That looks familiar. Looks an awful lot like what we had up there above. So let's do another one of these PTs. I do appreciate all 114 of you resisting the urge to ask what is a PT. I know for some of you that was really hard, much harder than the chemistry. So we have this guy, and then we're going to do exactly what we did last time. We're going to do that E2 thing that is all mysterious. Stands for bimolecular elimination. Not really, because you have the option. What is a PT? Yeah, you have the option to basically copy and paste stuff. So regurgitating mechanisms is not going to be a major component of the final. And that generates an acid. So we're there. So we went all the way from an alcohol to an acid. Okay, what I'm going to do now is we're going to get two reagents for the price of one. So I'm going to circle this water here. The reason I'm circling that is it costs everything. There's no other answer to that question anymore. And this water here. So we've needed water to make this hydrate, and we needed water to kind of do this final elimination. But this water here, you can imagine, can come from this guy here. We also, we've been chucking waters left, right, and center. But for this hydrate to happen, you need water. So there's another reagent we can use. And it's called PDC. Who cares? It's pyridinium. You know what? I don't even care about this. Dichromate. You know what? I don't want to actually get into the detail of it. What I want to say is that PDC, no water. Same as Jones, but no water. Sorry, I meant PCC. Fuck, I'll put it out there. I'm suddenly mind blanking, and I need to sketch this out because I'm having trouble with this all of a sudden. Okay, yeah, of course it is. You do not need to know this. What the really key thing here is that no water to make hydrate. Therefore, stops at aldehyde. My surface is really overheating. If it all starts going weird, it's because my surface is caught on fire. So, if we're looking back at this, mechanistically it's identical. You just have a chlorine here instead of an OH leaving group, you have a chlorine leaving group, but it's even better. We'll talk about leaving groups in a second. But if I go back to slide number 1, the Jones reagent can take us from an alcohol up to the acid, and or from an aldehyde up to the acid. And PDC takes us from the alcohol to the aldehyde. So we kind of have a way here to go all the way down, part of the way, or just the final step, all the way up, or just part of the way up. And to be perfectly honest, there is a way to go from an ester to an aldehyde. There's a reagent that does that, but both of them actually do it. I just chose to go with PCC. There are two of them, and they both do the same thing, but we're going to go with PCC. Just arbitrarily picking one. I think you need to know that PCC exists. But I'm not sure if I'm going to, know that it exists. We're changing. This one comes up, I think, occasionally on MCATs. And that's why I'm just touching on it. So there are ways to go from just the ester to the aldehyde directly, but that's actually not the way we mostly do it in the lab. We normally take the ester all the way down to the alcohol and then come back up to the aldehyde. It's more reliable, cleaner. So these are actually like the ways that you would actually do that. They're There are better ways than a Jones reagent. I don't want to get into the mechanisms of a whole bunch of really weird ruthenium catalysts and stuff, though. Okay. So, we can make acids, we can make aldehydes, we can make alcohols, we can go back and forth between all of those things. But then there were esters, and where the hell do the esters come from? So, how do you make an ester? You know, this is normally one of the first reactions that we give you guys if you're in the lab. So catalytic H2SO4 in methanol as solvent. This is called a Fischer Esterification, and it's named after Emil Fischer, who I have a massive man crush on, like offset by like 100 years and stuff, but because of course he invented more stuff. Really has to stop. So what's happening, and this is going to give us a methyl ester, and depending what alcohol we use, we'll get whatever is here, and you know what? Just to make that super clear, I'm going to switch colors because I can. Okay. Yeah, Fischer projections, Fischer esterifications, making sugars, all that stuff. Yeah, the projections are still a mistake. I've done a lot of useful experimental chemistry in Canadian chemistry and like done some stuff where I've studied like lab safety and things, but really the community knows me for hating Fischer projections more than anybody else in the country. Go to conferences like, hey, you're the Fischer projection guy. Okay. When in doubt, protonate something. Okay. So that has a resonance structure, obviously. We were just talking about resonance structures of aldehydes versus esters. We'll invoke it here. You don't need to draw the resonance structure, you draw this reaction directly on the starting thing. And then methanol, unsurprisingly, attacks that carbon. And oh god, that carbon is making 3 single bonds to oxygen. What is wrong with this? Now we're going to do a proton transfer. And we're going to remove that pesky water molecule. And oh look, and there's tons of methanol around. So this reaction is entirely in equilibrium. I should actually probably make all these arrows equilibrium arrows. They are. That one's definitely in equilibrium. So everything's in equilibrium. And I'm saying this is the product. You know, how am I saying that that's the product? And this is all driven by Le Chatelier's principle. go forward, use lots of methanol. Go backward, do it in water. Because you can push the arrows exactly the opposite direction, all the way backwards, and you'll go all the way back to the starting material. So you can make esters or you can make alcohol acids. So acids can turn to esters by adding an alcohol and doing this. Esters can turn to acids by adding water and doing this. And it's all based on how much of this product is there. You're drowning in methanol and you have very little water. So it drives towards producing water. Because here, there's this water molecule falling off. So there's one molecule of water. And if you go the other way, you'll have the methanol molecule falling off at this arrow. So this reaction can go forward and backward. And which way it goes all depends on, are you in methanol or are you in water? So this is how we can make esters. Okay, so all of this was really leading, all this carbonyl chemistry was really leading towards this next slide. Perfect, the timing is going to be great because I'm not going to finish. So we're going to finish the next class. And that's, what about amides? Yeah, you need to know this. So if this was an alcohol, we just drew that. Now I've just swapped an alcohol for a nitrogen. This does not work. Anyone know why this does not work? You can't, you do not, what I mean by does not work is you do not get this. Yeah. What does that have to do with anything? That's true. That oxygen is more electronegative. So it won't remove itself. Okay, not quite. You're on the right track, but you're on the right track with the electronegativity, but I think you're off the right track about removing yourself. I like where you're going, Muhammad Ali, but why does the nitrogen choose not to react? And that's not quite true. Nitrogen is going to react, it's just not going to react the way we want it to. Anyone else have a theory on this? You're right, the nitrogen is not going to react with the acid. So this comes down to the fact that I said this a few times, classes leading up to this. The fastest reactions out there are acid-base reactions. So you're going to make a salt. You're going to make a carboxylate salt of the ammonium. And now, what we just did with the Fischer esterification is we relied on this center here being positive. Good luck having that center being positive now when it's negatively charged. And then we relied on the oxygen having a lone pair to attack. It doesn't have a lone pair, it's now positively charged and it's lost its lone pair. So we have destroyed both sides of the equation. We have both made our electrophile less electrophilic and our nucleophile less nucleophilic, and there's no reaction. But of course, amide bonds underline all of life. Like, that's what peptides are. and peptides are formed by combining an acid and an amine. And so next class, we're going to wrap up carbonyl chemistry by talking about how we can get around this problem. We can do it in the lab. And then we're just going to envy nature for a moment. So after that, we are going to, this is all chapter, it's in the syllabus. I don't have the textbook right here. So I'm going to say it's in the syllabus. Yeah. Yeah. So on this thing here, if you look at what needed, we needed this. This is the key step right here. I'm going to just highlight this in green. So we needed a lone pair on the methanol to do the attack, and we needed the positive charge on the acid. And we got that because we protonated the acid, making it positive, and we had the lone pair on the methanol. And the reason this was able to work is because when you have methanol and this acid together, the most basic thing in solution is the lone pair on the acid. So this little bit of acid that's present goes on to the lone pair. Cool. So now our electrophile is positive. Our nucleophile is, it's not negative, but it's okay. It's got electrons. Now with the amide, this acid that we put in as a catalyst doesn't even come into it because the amine sees a carboxylic acid and deprotonates it. And so now that we needed this lone pair, it's gone because it's tied up in a nitrogen hydrogen bond. And we needed this to be positive. Good luck with that because now you got a negative charge on the molecule. So your electrophile is much less positive and your nucleophile is a lot less negative. Actually, your electrophile is negative and your nucleophile is positive. So you're kind of screwed. Does that make sense? Where the alcohol was formed. With the reduction with the lithium aluminum hydride? Dozy? Or this one? Chromium. So the acid, you mean? Mm-hmm. You had this slide, right? Anything in particular, or just like admiring the horrible penmanship? I'm going to upload all these slides online, so if you did miss anything, it's all going to be up there. And so will be the video. Why does the proton go to that one? It doesn't matter. It could have gone to any of them. What you'll find out is if it goes to, in a lot of places, you get stuck mechanistically. And it's a bit unfair. Well, it's not so much unfair as you need to start somewhere and you're starting here. So you get a sense for when you're going to get stuck, when things can't progress. Like in general, electrons flow from things with electrons to things that want electrons. And occasionally you just get stuck in a well where, there's nowhere to go but back because the electrons don't have anywhere to go. We ended up not getting stuck. So I basically walked the proton around to make sure that I could get my electrons to go where I wanted them to go. Now that proton's coming off and on all the time. In the third step where the hydrogen come from, there's acid in solution. So just grab an H plus wherever you want. There's tons of them around. I don't think, yeah, there's just tons and tons of H plus, like there's sulfuric acid and chromium. Okay. Yeah, everyone have a really good day, and I will see you on Wednesday. Take care. Bye.